Hello, everyone. Slight technical difficulty, but now it's fixed. My name is Scott Grizzard. This is Calculus 2311, Section 1 from the University of South Florida. So last time we talked about the min-max function, and then we took a test on Saturday. As for the grading, there's one question left to grade. The grades were, still one question left, but the grades are fairly good. It looks like we're going to be number 2. Robert beat us. Marion may beat us. We're kind of close to Robert, and I don't know what Marion's grades are yet. There was a little bit of fall off that, of course, that was to be expected. We went online from last year. It wasn't bad. Right now, the average is like around the 72. So, I mean, it is what it is. There were several distracting things on that quiz. And then if any of you want to send me an email, the testing procedures need tweaking. They weren't all that great. So if you guys have any suggestions on how to make the tests go more smoothly, I am all ears. Apparently, having Discord on both the computer, having Discord running on your computer while you were taking the test seems to have caused a lot of problems. Whereas if it was on your phone only, that seemed to have worked better. So we'll talk about the testing procedure at some point again. And again, if you guys have any suggestions, I am all ears about how to make that process more smooth. It's the first time for me to doing this, and for the remote stuff. Are there any questions before we get started today? Okay, so someone says smooth. Okay, so the final exam. The final exam is not optional. There's only a test 4, right, which is the final. And it's not optional, it's required. It counts twice in the grade book. Okay, it counts once as a final exam, the final exam, the 20%, and then it counts as a test 4. So it's the exact same exam, but the score goes in twice. Now, if you're if it's lower, this almost never happens for my classes. My classes do very well on the final. But if it's lower than your other 3 test scores, it only counts once. If it's higher than your other 3 test scores, then it will replace your lowest test score. But it also counts as the final. So it counts 20% of your grade on your own. And then it could count another 15% if it's higher than your lowest test score. Which tends to happen in my class. The people do very well in the final usually in my class. Some of the other classes, it's not always true. And that wasn't always true for me either. So, yeah. And I know that's confusing as can be. But that's the way it's set up. So it's not final. A curve, there's basically, the problem is that 3 of the classes did extremely well on the test. By extremely well, we mean a median that was over 70%. So, which is good for test 3. It's not as good as I'd like it to be, because, I think my scores would like drop 5%. Robert managed to have not lose any of his. He has his averages are in line with what they were last year. I need to figure out what he's doing, because he managed to maintain his grades. But anyway, so no, there's not going to be a curve. Don't expect one. Has there been talk? Sure. Some of the other instructors that did very, very poorly, they've been talking about it. But, the problem is that there are sections that just maintain the average. So, what the curve is going to be. So, there's one question left to grade. It is that I need to grade. So, you'll have there's one question. It's been graded, but I need to check the grading on it. So it'll probably be Tuesday before all the tests you'll probably get your test back tomorrow. There's people taking the makeup today. I mean, does it really matter because you have the PDF already? But we're trying to do the whole not release the grades until people have taken the makeup thing. So, any other questions? Okay, so all right. So that seems to be it. So here's what's going on. I do things. So for the third exam, I'm the only one who does the. Well, I'm not the only person that does it. Robert does it too. But I spend the whole time doing the. So yeah, the scores are good. The scores are above 70. I mean, not all the scores, but the median's above 70, and it will remain above 70. And and I'll talk about that ad nauseum if you want to, but I'll do it in chat, not over Twitch. So anyway, I do things a little bit differently for the last module, and it works. So I'm going to stick to doing it. What I do is I flip the order. So most of the people today are talking about antiderivatives. We're going to jump right into the area under the curve because the area under the curve is directly related to the antiderivative. So we're going to basically start at the end and work backwards. This seems to work very well in the past. This seems to be a method of doing this that people like, and it gives you better instincts for Calc 2 about what's going on. So let's just start with that. So today so last time we talked about this thing called the minimum and maximum functions. Okay, and just recall that there was this weird definition of the min-max function. Okay, so let's just do the max. Recall that there was this function called max, right, with an f and a as parameters, right, which equaled this weird thing. The max of f of t such that t was in ax if x was greater than or equal to a max f of t, the t was in xa if x is less than a. All right, so how do we feel about that function 1 to 5? Okay, so I don't have a TA today, apparently. Let's do the, sorry, 5. All right, so how do we feel about this function 1 to 5? This is the one we talked about last time. Okay. All right. So today what we're going to talk about is something called the area under the curve. And here's the motivating question behind it. So let's see, let's just write this. This was parameter function, and this was parameter. Okay, so here's kind of the motivating question behind the whole module. So what is the formula for the area of a circle in terms of radius? There we go. So the area of a circle is A equals pi r squared. Now, what is the formula for the circumference of a circle in terms of the radius? I probably didn't spell that right. Yeah. C equals 2 pi r. What is the relationship between these two functions? What is the relationship between pi r squared there and 2 pi r? Yeah, why is that? Yeah. C is the derivative of A. And the question is why? Why is this true? So there's the question. Why is the derivative of the area the length of the boundary? Okay. That's kind of a motivating question. All right. So it has to do with this idea of bounded area. So let's talk about the area under a curve. This is this function, okay? And we're going to call it AUC. So we're going to have a definition of this function. So 1 to 5, how do we feel about this idea that what I have is the area? What I have, these two, one function is the derivative of the other, and that what I'm talking about, the derivative is the formula for the boundary. How do we feel about that? Right? And this only works for a circle. A circle is a very special one parameter type object. Well, it will work for other things, but you have to modify what you're talking about slightly. But for this particular thing, for a circle, it's beautiful, right? 1 is the derivative. Okay. Okay. Did I spell it wrong? Okay. What is the length of the boundary? Okay. So what we're going to do is we're going to define a new function called the area under the curve. So we're going to say let d be an interval. And let f be continuous. And this is actually important. And let a and d. That should be a D, by the way. It's not a very good D. Looks like the D in Walt Disney's signature, right? Looks weird. Okay. And let A be some point in D. Okay. The area under the curve function Yes, that is AUC, area under the curve. It measures the sine area between the graph of f and the x-axis from the base point A to x. Okay, so let's look at what this looks like here. Okay, now I've got 3 computers going on in order to make this broadcast happen, so no promises that some of them won't crash. Let's look what it looks like. So here I've got a function. Here I have a function. This program is Maple, by the way, that's producing this animation. And here my base point, if you can see it here. See if I can zoom in a little. It will let me. Okay, so here my base point, if you can see it, here my base point is 0, and I'm going to start at x equals 0. So right now, and my function here is 1 plus cosine of t. Okay. So how do we feel about this? 1 to 5. What's about to happen? Oops. So 1 to 5, how do we feel about what's about to happen? What I want to do is I want to measure the area under this curve from 0 into whatever point I have. So this function is going to measure that area for me. So here's how it works. All of this is positive area. So see here, right now, when x is 3, this thing is measuring the area from 0 to 3, okay? And that's all this area that's shaded in green. So right now, f of 3 is basically 0, right? I mean, 3.14, f of pi is basically 0, right? Is everyone on board with that? But now what I'm going to do is I'm adding this area. And yes, you did it in pre-calc with tables under the back of the book. But now we're going to show you where that table came from, okay? And that table depended on a very particular function. We're going to do it for functions in general. And this function is very, very, very important, not just in math, but it's the notation. I'm the only one who does this notation, by the way, for this function. There's another notation that is much more common in mathematics. This notation, AUC, you only really see it in pharmacokinetics books. So you only really see it in medical schools now. Everyone else has just gone to a different notation, and I'll cover that notation as well. But this notation is a little bit better for our purposes today. So this measures the areas here. So right now, f is way down here, okay? Way down here at the y value right now is 0. But this thing has swept out the area under the curve from under f from 0 to 3 is 3.14. Okay? And then it will keep sweeping out area as I keep going. As you can see, as x increases, a stays the same, but as x increases as we go here, right? A is over here. It's always the same, but as x increases, it sweeps out more area behind it. How do we feel about what this function is doing? 1 to 5. How do we feel about this function? It's measuring this area that's being swept under the curve. And notice here that f exists, the graph of f. The graph of f exists before we do anything to the curve, okay? Now, the only condition that I have on this function, I have 2. the function must be continuous, and it must be defined over an interval, okay? Or the piece that we're talking about is an interval, okay? I don't care if it's open interval, closed interval, don't care. Function must be continuous, it must be continuous over an interval, and A must be in the interval, okay? And then we're talking about every x within the interval, okay? So that's the idea. F can be any function that's continuous, any continuous function. You give me x squared. This particular one is 1 plus cosine. I can do others. Here's the log, and these things take a little while to compute. But let's do the log of this thing. So let's do the log of t plus 1. It's thinking about it, it's thinking about it, it's thinking about it. F must be continuous. That was written here. So let D be an interval. But the really big thing is that F is continuous. But D is an interval, A is some in B. And that's the base point, okay? How do we feel about that? You feel better about it now? Okay. Let's look at another one. Here we go. Here I've done the natural log of t plus 1. So if I run the area under the curve function, right, this is an always increasing function. I don't know why it's doing that. It should not, the function should have been displayed before. Why is it doing that? I probably have a bug in my code. Ah, I do. Oh, that goes there. This goes there. Control E. Ah, now I've really messed it up. What'd I do wrong? 2 parentheses, close, area plot, close, then the graph. So it should be close, close. So plot, func, open, open, 1, 2, 1, 2. Ah, there it is. Let's try that again. Okay. So, nope, it's got an error. Sorry. Let's see if this one will run. Nope, they're all going to have the same problem because I didn't put the things in. Okay, sorry about that. I didn't put the code in right. Here we go. Let's do this one. So this idea of signed area. All right, I'm sorry about the bad code. This idea about signed area. Is like this, okay? So I start here. Now, when I'm above the x-axis, whenever I'm above the x-axis, okay, I have positive area. But whenever I'm below the x-axis, I have negative area, okay? So what I'm going to do is I'm going to subtract area if I wind up below the x-axis. All right, and you can see that right here. Here, I've started the function in the same place. All right, I've started the function in the same place. But now, so right here, I dip underneath, and again, the curve should be displayed the whole time, and it's pissing me off. Let's see if I can get issue another one. I had all of these set up on my computer in my office, and I forgot to commit them, so now I'm running a little blind. So let's see what happens. It's thinking about it. Okay, so I have signed area. So if I'm above the x-axis, okay, ignore this picture. This picture's bad. Oops. Okay, control, execute. Oh, this was the one I should have done the whole time. Okay. So I have this idea where if I dip below the x-axis, I have negative area. Okay? How do we feel about that idea? This is signed area, so I can have negative area. 1 to 5. How do we feel about this idea that I can have negative area? Okay. So what I'm going to do is I'm going to accumulate area. Is everyone on board with this kind of idea? I hate that I can't see the shocked and disappointed looks on your faces, but I'm seeing good numbers on there. So we're going to go ahead with it as if people are happy with this idea. Okay. Now, notice something here. Notice how my function, whenever my function is above the graph, okay? Notice that whenever my function is above the graph, oh, a little bit, okay, the reason why is because I'm using the trapezoidal method to draw these things, and in order to make the things happen, there should not be that little bit of red, okay? And if you look at it, I'm sorry about that. If you look at it, right, the little bit of red goes, see? There's no red now, and then there's red, and then there's no red, and then there's red again. And the reason is because of the way I programmed the thing. So I couldn't make it be perfect so that it would work for every function and still compute in a reasonable amount of time. If I wanted to make it better, I would let it compute for 3 days before it displayed the graphic, but then the graphics would be enormous. Does that answer your question on that? So ignore that little bit of red. That's bad red. Before. Okay. So I'm adding curve. Now notice where this thing has, right? So when I'm moving to the right, whenever I'm above the curve, okay? Whenever x is above the curve, notice something here. Whenever x is above the curve, if I move to the right, I'm going to accumulate more area, okay? So if I advance this a frame, notice how I'm adding more area, right? My function is decreasing, but as long as I'm above the curve, I'm adding area. How do we feel about as I move to the right, As long as I'm above the curve, I add area. How do we feel about that? 1 to 5. Okay. Let's write that down. I don't know if it's possible to copy this, by the way, into the thing. Let's see. That would be just too cool for school, wouldn't it? Yep. Well, this let me paste. Guess not. Okay. It won't let me paste. So notice some properties of this thing. Okay. That would have just been too cool. If it would have let me paste an animated GIF, that would have just been too cool. So some properties. Exactly. So if x is greater than a, then the following. Oops, sorry. Thank you. So if x is greater than a, if f of x is greater than 0, I'm adding area as I move to the right. And if f of x is less than 0, I'm going to be adding negative area. In other words, I'm subtracting area as I move to the right. Okay? In other words, if f is greater than 0, then AUC AF of x is increasing. If f is less than 0, then AUC, oops, that should be an FA, not an FA. FA, FA of x is decreasing. That's interesting. How do we feel about that idea? 1 to 5. If I'm above the x-axis, I'm accumulating positive area. Whereas if I'm below the x-axis, I'm accumulating negative area, so I'm taking area away. In other words, if I'm above the x-axis, then AUC is increasing. Whereas if f is negative, AUC decreases. It's a little suggestive. Okay. Let's go pull another property here. Let's go look at another one here. Now, look at what happens right here when x is 2 here. Right? F of 2 is 0. Now, I've accumulated all of the positive area that I'm going to, right? And now when I hit play again, I start accumulating negative area, so I start subtracting area, right? My number starts going down. So where does AUC have the maximum? It's not when F is maximized, right? If F is maximized right here, I'm still accumulating positive area if I move to the right. So when does AUC have a maximum? Yeah, when it crosses the x-axis. In other words, when F goes from positive to negative, AUC FA has a local max. How do we feel about that? 1 to 5. Right? When I cross the x-axis, yeah. It's not just like a derivative graph. It's not just like a derivative graph. Someone's saying it's like a derivative graph. Oh, it's more than just like a derivative graph. We have a name for this theorem. This is the big one. It has two parts. The first part, if f is continuous on the interval d, then d over dx of AUC FA of x equals f of x. That's the first bit of it. There's also a part 2. Let's come back to that in a minute. Okay. So let's do another example. This one a little bit more, basic. We're coming back to that idea in a minute. This is part 1. There is a part 2. Okay? Let's let f of x be something a little bit simple. Let's let f of x equal to x. Now let's let a equal 0. All right? So let's draw the graph of this real fast. I don't know why it wants to print in highlighter. That's annoying. And now it won't drag. All right, someone smarter than me in OneNote. Tell me why it's being mean to me. Let's do this one more time with feeling. Okay. No, it won't even let me right click now. Oh, I see. Okay. Let's do f of x equals 2x. Okay. What does the graph of this look like? Let's make it so that it intersects nicely. What does the graph of this thing look like? If x equals 1, what's y? Right, positive and it's 2, right? So the graph looks like a straight line here. Let's see, view, draw. There it is, ruler. My graph looks something like that. Okay. Now, what is AUC F0 of 0? What is the area under the curve starting from 0 and going to 0? Yeah, right? There's no width. I've got no height and no width. More importantly, I've got no width. Okay? Now, what is AUC F0 of 1? Okay, so that's this area right here. Ooh, let me get a highlighter here. No, give me a new pen. I want a highlighter. I went to green highlighter, and I want it to be very small. So I swept it out that way, and I got that amount of area. What is that? Well, is it 2? How would I find that area? What is the area? What is the shape of this thing? It's a triangle. So how would I find the area here? Okay. Well, what is the area? Well, the area would be 1/2 the base, all right, which is 1. So we're going to call that h for width. Times the height, which we're going to call y. And if you're wondering why we're calling the base h, it's because of the French. just to piss you off, we're not going to use W for the base, right? Because that would be the logical thing to do, but it's French, so we have to use H. It's H for width. But this width is what? It's 1. And then the height is 2. That equals 1. Well, what is AUC F0 of 2? So if I go to 2, yeah, I'm going to wind up at 4, right? The base times the width, right? Instead of height, we're going to call it the width. And the width here is 4. So that equals 4. Now, what if I take an arbitrary x? How would I find the formula for the AUC for this particular number? Well, it'd be 1/2, right? No, don't mention the word antiderivative. We don't care yet. Someone took BC in high school. Let's just work out the formula. Okay? It'd be 1/2 x times what? This is the base. Okay? What's the height? The y value, right? Well, in this particular circumstance, what is that? That'd be f of x, correct? So what was f? F was 2x. So it'd be 1/2 times x times 2x. Okay. How do we feel about that, 1 to 5? Y is height. Okay. It's rather interesting. And of course, I take the derivative of x squared. All right. Okay. And I wind up there. So that's my fundamental theorem of calculus, part 1 again. Oops. How do we feel about that one, 1 to 5? Okay. No, I'm not solving for x. I'm just running through some stuff about this thing. Well, let's look at this again. Let's ask ourselves the next question. What happens if I want to change this base point? Instead of this, oops, I wanted you. Let's do the base point of 1. All right. Let's see. Can I make this line up just like it did before? Yes. Okay. Close enough. Okay. Let's change the base point. Let's change the base point to 1. Okay. What is AUC F1 of 2? So now I'm talking about the area from here to here. Yeah, so I don't change the graph. The graph is still 2 squared. But what I've done is I'm changing the base point. Instead of 0, I'm going to use 1 as my base point. Okay? Now the question is, how does this change what we're talking about? So how would I compute this? Well, let's see. I could do a rectangle triangle, so I could take this bit here and add that bit there. But I could also do this. I could take this area here and I could take the whole area in yellow, and then I could subtract this triangle here. Right? So I could take this whole area here, and then I could subtract this area here. In other words, What's the area of the big one? So in other words, I could take the area of this triangle here and then subtract the point I don't want. So this big triangle here is 1/2 the base, which was 2, times the height, which was 4, minus the bit I don't want, and that would give me the area of what I wanted, right? Crap. The notification bar just came up on my tablet, and it's bothering me. In other words, this here was AUC F1, F0 of 2. And this part here was AUC F1 of, sorry, AUC F0 of 1. What'd I mess up with? You're right. It's too early for math. Okay. You're right. It's supposed to be 3. So in other words, I could take the whole thing, the 4, and then subtract out the small triangle. How do we feel about that, 1 to 5? Okay. Which gives us another way to do this, right? Which is the following. I could have also said this. So let's say this more generally. AUC F1 of x equals what? If I just wanted the area under the curve function at this point, what could I do to get it? The question is, why didn't I just do the area of a trapezoid? The reason why is I want to make a point. Okay, and I'm using a very simple example so that we can actually do the computations. Right? Triangles are easy to work with. Well, what's the point? To calculate this, I take AUC F0. How would I do this? What would be the formula? It'd be 1/2 correct? Now this right here, x times f of x minus 1/2 times 1 times 2. In other words, what I did was I took AUC, in order to calculate when the base point was 1, I took AUC F0 of x, and I subtracted AUC F0 of 1. Now, how do we feel about that, 1 to 5? I think I just lost some. Yes, so when I change the base point, I'm going to do a shift. And in order to do that shift, what I'm going to do is I'm going to subtract the other one that I have. How do we feel about that, 1 to 5? I probably just lost people. Okay? This is a step on the crazy train. Notice one other thing. Oh, that's so nice of you to see. I've showed you weirder stuff. Okay. You don't know how much that warms my heart. Okay. Notice that this is just a number. Is everyone on board with the fact that that's just a number? Okay. This piece here is just another word. Right, so the values came from plugging x into the, so here I've got AUC F0 of x. And x, I don't know where it is, but it's an abstract x. And now what I've done is I've subtracted this number. So I wanted to know, okay, there's no way for me to get in there with an eraser. Okay. I don't think there's any way for me to erase that. So what I wanted to know was the area in green. Okay. I want to know the area in the green. So what I'm going to do So 1 to 5, how do we feel about that? But this means that's true for any base point, right? If I want to do any type of base point shift, I now have a way to do it. Right? I now have a formula to do any base point shift. So to move from yes, what happens if A is -1? Does the formula still hold? That's a good question. Okay. How do we feel, though, about this formula right here, the one I just wrote? But remember, I'd be subtracting a negative number. And notice again, this is just a number. Okay. Let's ask one more question. Give me any antiderivative. So give me any function whose derivative is x squared. I'm sorry, whose derivative is 2x. Give me a function whose derivative is 2x. Okay, so here's one. I'm going to modify it a little bit to get rid of your 3. Let's do x. Let's do x squared plus 5. Okay? So let's let g of x equal x squared plus 5. Okay? Now, I maintain then the following. I maintain that there is an A, so that g of x is AUC FA of x. Okay? And this goes back to the negative question. What if I wanted x squared plus 5 to be the, for what A would x squared plus 5 work? Moreover, I maintained that I could get this formula from that. Let's start with the first one. Okay? Let's start with this part. I claim that AUC FA 0 of x equals g of x minus g of 0. Okay? Let's do this part first. I may get to this part, I may not. This is the more important part right now. I maintain that I could get there. How do I do it? I say that this function equals AUC FA of x. Okay? How do we feel about that part, 1 to 5? I'm not going to make it to the other part. 1 to 5, how do we feel about that part? The 5s there cancel. So now we get to the first zone. Then, for any x in A, sorry, x in, for any A in D, and any x in D, the first part holds, and then the second part holds. AUC FA of x equals g of x minus g of A. So I claim that that's true in general, and there's the second part of the fundamental theorem of calculus, okay? Let f be defined on an interval D. If f is continuous on that interval, then for any A and any x in the interval, the derivative of the AUC function is f of x, and for any antiderivative of f, in other words, for any function g defined on D so that g prime equals f, the AUC function fa of x equals g of x minus g of a. How do we feel about that, 1 to 5? Yeah. So we'll get into that. We'll get into what happens when I have base points to the left and to the right tomorrow, Wednesday. Okay? We didn't do that, and we've only started to scratch the surface because we've only done circumstances where x is greater than a. We also need to handle circumstances where x is less than a, and we haven't done it yet. We will deal with that on Wednesday. But how do we feel about this? Okay. Couple words. This is the key. I know I'm out of time. This is the key to Module 4. Okay? You will see this statement on every quiz, and I do mean every quiz for the next 3 weeks. Okay? The quiz on Wednesday is going to have it. The quiz next Monday will have it. The quiz next Wednesday will have it. And the quiz, both quizzes during the final week of class will have this. State the fundamental theorem of calculus. Is it going to be on the test? Let's see. What's it called again? The fundamental theorem of calculus. And what's this class called again? This is called the fundamental theorem of calculus, and this class is called Calc 1. Yeah, it's going to be on the final. Okay, now, couple questions about the test. The final exam is cumulative. It's about, and I'll explain more about this tomorrow, but what the final exam would have to be cumulative anyway by its very nature. Okay, there's only so much that we wouldn't have to ask you anyway. All right. Is there any other questions? I see confusion over this idea that there's a shift under the thing, so we'd be subtracting area. Yes, I will get into this more on Wednesday. But just to review, we covered the motivating question, we covered the AUC function, and we covered the fundamental theorem of calculus. We started it. All right. We are going to prove the fundamental theorem of calculus before we're done. That's actually kind of been where the course has been building, and it's going to be one of the last things we do. All right. Now, I'm doing something here. As I said, I'm skipping part of the antiderivative bit. We're going to pick that up as we go along. I'm also kind of starting at the end. And the reason why I'm doing that is because everything, well, not everything, there's still stuff, from the other stuff. But almost everything that we're going to do for test 4 comes down to the fundamental theorem of calculus. So instead of doing it on the last day, we're starting with it, okay? Are there any questions, comments, issues, suggestions, thoughts? Okay, I'm going to hop. So I will see you on Wednesday. You're welcome to stick around for the next one because I'm going to kind of reorder things a little bit. But what we're going to do is I'm going to jump in voice chat on Discord if you have any questions. That's it.